Okay, so we're going to cover 4.5 and section 5.1, and what I hope will be a short video. I know I'm competing against the Super Bowl today, so, what are you going to do? 4.5 is about substitution, so if you have seen substitution before, then you can skip to the end of this section and look at 5.1. What I encourage you to do, though, is actually, if you have seen substitution before, there's a technique involving definite integration using substitution that I would like for you to see that you may not have seen if you've seen substitution before, perhaps in high school or another class. Anyway, I'll be more specific when I email the video link to the class. But let's just start off. So substitution, the idea behind it, this is an integration technique. I already can't spell substitution. This is an integration technique, and it's meant to undo the chain rule and the chain rule, of course, what you do when you take the derivative of a composition of functions. So here's the example. So if you have a function inside of another function, so you composed f with g, and you want to take the derivative of this, well, what do? The chain rule says you take the derivative of the outside function, and then you multiply by the derivative of the inside function, like that. So an example of this might be, suppose you wanted to compute the derivative of x squared to the 7th, or x squared plus 3 to the 7th power. Then this is, you take the derivative of the outside, which is just raising something to the 7, so you take that derivative, bring the 7 down, drop the exponent by 1, and then you multiply by the derivative of the inside function, which is 2x. Okay, so now, of course, this would never be written like this. It would be written as 14x times x squared plus 3 to the 6th power. Okay, now the idea is that, now flip this situation. Suppose you wanted to integrate. Okay, so if you wanted to integrate, find the definite integral of something that looked like this. So you're integrating this function here, and you recognized that someone used the chain rule to take this derivative. Then you could rewrite this as taking the antiderivative of a derivative, okay? And so, as we know by the fundamental theorem of calculus, these taking derivatives and taking antiderivatives, this is an inverse operation to each other. So we can just essentially take the derivative and the integral and erase the two of them, and we would just have the answer to this integral, right? So in our example here, we would know that, so if we saw something like 14x times x squared plus 3 to the 6th power, then we would say, oh, this is the same thing as the integral of the derivative of x squared plus 3 to the 7th power. And so we could cancel the differentiation and the integration to get x squared plus 3 to the 7th power plus c as the answer. Okay, but how do you do this? I mean, like, that's like looking at this and saying, oh, this is somebody took a derivative using the chain rule. Getting from what's in here to what's in here is a little bit takes a little bit of work. The idea is that you should always look for something in the integrand that looks like the derivative sorry, I can't write today. Look for something in the integrand that looks like the derivative of something else in the integrand. I'm just curious. I'm going to look and see, does that show up? Oh, it just shows up. Okay. we take a look at the integral, look in the integrand, and we look for something in here that looks like the derivative of something else in here. So what I see is I see x kind of looks like the derivative of x squared plus 3. It's a constant times it, but like x is basically the derivative of x squared. So that's the idea behind substitution. And so we're going to take a look more concretely at this, so the steps in this process. So the first step is we notice that x is kind of almost, this symbol means almost, the derivative of x squared plus 3, okay, almost. So we create a new variable, which usually u, sometimes it's w, it doesn't matter what you call it, and we take this thing which somebody took the derivative of, and we set it equal to a new variable. Then we take the derivative of that variable, okay? So if we do that, we get du dx is equal to 2x, right? This is usually written in the form that makes it more convenient for using this technique of substitution, which is we pretend that this is a fraction and we multiply the dx over to the other side. We'll see why this is important in just a minute. Okay, so now let's look at this example, the 14x times x squared plus 3 to the 6th power dx. Okay, so suppose we wanted to look at this. Now, we've recognized that x is kind of the derivative of x squared plus 3, and so we substitute. So this right here, if u is equal to x squared plus 3, then x squared plus 3 to the 6th power, this is u to the 6th power. So we write that as in, the integral as u to the 6th power. We leave everything else the same. So notice we've left the 14 times x and the dx symbol the same, but we've replaced this part here by its counterpart with u, okay? Now we want to do exactly the same thing for everything that's left here. So this right here and this right here, they are 14x dx. And here now we look at this equation here. We see that every time we have 2x times dx, that's the same thing as du. So how do we get that? How do we get 2x times dx to look like du? Well, we just multiply by 7. So 14x dx is equal to 7 times du. That comes from this equation right here. Okay, so we just looked at that and said, well, what do we have to do to make that 14x instead of 2x? And we just multiply both sides by 7. Okay, so now we're going to take this piece and this piece, and we're going to replace them by du. So we get 7 du, I'm going to write du at the end because it's an integral, and then we leave the u to the 6th part alone here. Okay, now notice we've covered everything in the original integral here, so we now can integrate this. So this integrates to be u to the 7th, let's just raise the power, and then we add a constant of integration. And now we're just about done. We just have to replace u by what it was in terms of x. So this is x squared plus 3 raised to the 7th power plus c. Okay. Now if you look at this, if you take the derivative of this, you will get what's here. So this, we could always check this and see that if you take the derivative with respect to x of x squared plus 3 raised to the 7th power plus c, that this will be, well, we'll just use the chain rule, so we get that, and then we multiply by the derivative of what was inside, so we get 14x. So notice our answer to this question is the most general function whose derivative is what was inside of the integral here. That's just indefinite integration. Okay. This process is the same for all substitution problems. So let's do another quick example. X cubed times cosine of x to the 4th plus 6. Okay. Again, we look for something in here which is the derivative of something else in here. So what I see is x cubed is almost the derivative of x to the 4th plus 6, okay? Notice I took the largest thing. Like this was actually, I could have just said this was x to the 4th, but I took the biggest thing in here whose derivative was kind of like x cubed. If you take the derivative of this, it's just, I mean, it's a constant times x cubed. So this determines our u. So u is equal to x to the fourth plus 6. We have this process where we take the derivative of this equation and we get 4x cubed, and then we change this equation to help for the substitution technique. So 4x cubed dx, like that. Okay, now we rewrite the integral, x cubed cosine of x to the fourth plus 6 dx. I'm going to use this and this equation, these two equations here, to change this so it contains no more x's, and then we'll do the integration. So the first thing I see is u is x to the fourth plus 6, so let's replace that. So we get x cubed times cosine of u dx. All right, very good. Now, that took care of this piece right here. Okay, now we have to account for x cubed and dx. But take a look, x cubed dx, all we have to do is divide away that 4. So 1/4 du is equal to x cubed dx. We use the second equation here with what's left over in the integral. So anywhere now that we see x cubed times a dx, we can write 1/4 du. And we do that. So we write 1/4 cosine of u. And again, I write the du at the end because this is an integral, and we put that symbol at the end. So now we've gotten that piece and that piece. All things involving x are gone from this integral, and now we can integrate. So the answer is 1/4 sine of u plus c. And to be really, really done, we need to go back and plug in x, because our answer to this should be a function of x. So this is x to the fourth plus 6 plus c. Okay, so this is the answer. All right, that's another example using substitution. Let's do another example. So the integral of the square root of 2x plus 1 dx. Okay, here, difficult to see what the u might be, but the choice in this case, if we want to try to use substitution, is to pick this. The reason for that is because du dx in this case will just be 2. So that means that we have du is equal to 2 dx. And that's a constant times dx. So if we took a very close look at this, once we substitute u in for that expression, all that's left is the dx symbol containing x's. And so this is a natural choice. More and more questions done like this will make that choice a little bit more clear. But let's integrate this. So we write the square root of u, we've replaced that by u, and we still have a dx here. Dx is equal to 1/2 of du, so we can just see that by dividing away the 2. So everywhere we see dx, we write 1/2 times du, and so we get 1/2 times the square root of u du. Okay, and now we've accounted for this piece. We've accounted for this piece in the integral, so we can integrate u the square root of u is just u to the 1/2, so we write 1/2 u to the 3/2 is how we integrate this. And we divide by the new power plus c, and of course if you simplify this you get 1/3 u to the 3/2 plus c, which is 1/3 times the quantity. So u is equal to 2x plus 1 to the 3/2 plus c, and this is a function whose derivative is the square root of 2x plus 1. Okay. Another example. Here, I'm going to just switch the letters a little bit. Sometimes you'll see, if you have a fraction, you may see the d with the variable written in the numerator of the fraction. This just is standard notation. So if you imagine the dz just out there. This is the function that we're integrating right here, that function. So here, z is kind of the derivative of 1 minus 4z squared, kind of. That derivative is minus 8z, okay? So notice it's just a constant times that. That's what we mean by almost. So this determines our choice of u, 1 minus 4z squared. Again, notice I took the biggest thing in the integrand, the biggest function whose derivative was a constant times z. Now du, I'm going to skip the multiplying over step here, and we're just going to write that. And now this determines our integral. So we have a square root of u in the denominator. That handles the denominator. And then everywhere we see z dz, we can use this equation here to determine what that has to be with u's. So notice, if I divide away the minus 8, then I get z dz here. So let's just take that constant, divide it over to the other side. So everywhere we see z times dz, which we do in the numerator, we write that. So minus 1/8 du. And then we integrate this. So this is, well, let's see. So let's simplify it a little bit first. This is u to the minus 1/2 power du times the constant 1/8, minus 1/8. And so we keep that as it is. Raise this power by 1. So that makes it a half, divide by the new power, divide by a half, plus c, and then you simplify a little bit here, you get minus 1/4 u to the 1/2 plus c, which is, let's see, u was 1 minus 4z, so we get minus 1/4 the square root of 1 minus 4z squared plus c. Okay. So this is our technique. All right. Let me show you one example of how to use this technique for definite integration. So go back to an example where we have the same function that we saw in a previous example, the square root of 2x plus 1. But now I'm going to put limits of integration on this integral. So this is a definite integral. So our answer should be a number, but the technique is the same. 2x plus 1 is the substitution. Du is equal to 2 dx. Here's where we might vary this a little bit from what you have seen maybe in high school or in a previous calculus class. These 0 and 4 represent x values, so I'm going to just indicate that they're x values here. And then we had, what, u to the 1/2 power, and then we divided by we multiplied by 1/2 du, which everything in the integrand here came from this stuff. We did that in the previous example. Now, I want to change these limits because I have u's here. I want u values here. But here's how we do it. So notice when x is equal to 0, that means that u is equal to 2 times 0 plus 1. So u is equal to 2 times 0 plus 1. So that means that u is equal to 1. So we're going to change this to make that a 1 down there. And when x is equal to 4, do the same, use this top equation. 2 times 4 plus 1 is 9, so u is equal to 9. And so we get u is 9, and we get a half u to the 1/2 du. And now we can perform this integral, we can compute this integral just using these numbers, and we can forget all about the x's. So at this point, forget x forever. Okay. Some of you may not have seen this technique before, but it's very straightforward. So when we computed this integral, we got, let's see, so we had 1/2 u to the 3/2 divided by 3/2, and we're integrating this from 1 to 9. So that was 1/3 times u to the 3/2 from 1 to 9. And these are u values, remember? So we can just plug this in, and we get 1/3, 9 raised to the 3/2 power minus 1/3, and then, well, 1 raised to the 3/2 power, but come on. And so this answer, if you work it out, it's 26/3. Okay? Notice, we lost the minute we changed the x values in the limits of integration to u values in the limits of integration. We forgot about x forever when doing a definite integral. I want you to do it this way in class. Okay. That is section 4.5. Now, I want to talk very briefly about section 5.1. So this is about areas between curves. Okay, here is the schematic picture. So I want to imagine two graphs. Let's call them f of x and g of x. And I am interested in the following quantity. So here's b, a. I'm interested in computing that area between this graph. Okay, we're going to do this using integrals. Okay, how do we do it? Okay, so recall delta x is b minus a over n, and we're going to cut this up into n pieces. And what I want to do is I want the formula for the area of one rectangle of that height. The xi's are the same. Okay, and the area of a rectangle in this picture is just, well, it's delta x, which is the width. Okay, and then we're multiplying by the height, which is the x value in f here minus the x value in g here. So this is f of xi minus g of xi. So this is the height, and this is the width. And we integrate exactly as before. So the area of this is going to be the limit, as n goes to infinity, of the sum, I goes from 1 to n, of f of xi minus g of xi times delta x. Okay? If you compute this limit out, which we will not do, we're going to use the rule, because in the limit it becomes an integral, and this becomes f of x minus g of x dx. This is the rule that I want you to know. Okay. This rule, not even going to do examples. We're going to work on examples in class. That's all for today.